Okay. So we talked about the ratio test on Friday. So the ratio test, you take the term in the series, a sub n, and you take the ratio of a sub n plus 1, so that's just n plus 1, substitute in for n, and take the ratio of a sub n plus 1 over a sub n, and if the limit as n goes to infinity of that ratio, the absolute value is less than 1, then it converges. If the ratio is greater than 1, it diverges, and if it's equal to 1, you have to use another test to figure out what's going on. So we looked at one example, at least, I think. A lot of times the ratio test is the only one you can use when you have things like exponentials or combinations of different kinds of functions, also factorials. And then we had the root test, which we didn't look at any examples. And the roots test says if you have a sub n, and usually this is only useful when a sub n is raised, all of a sub n includes something raised to a power. And then you take the nth root to basically get rid of that power, and then you look at the argument and see if the absolute value is less than 1 of that argument as n goes to infinity. And if it's less than 1, then it converges. If it's greater than 1, it diverges. And if it is equal to 1, then that test cannot tell you. You have to use some other test. So let's look at an example for that. So here we have the summation from n equals 1 to infinity of 2n over n plus 1 to the n power. So you can see that we've got this whole quantity raised to the n power. So what you do is you take the limit as n goes to infinity of the nth root of 2n over n plus 1 to the n power. And so the nth root of something to the nth power is just what we're originally raising to that power, so it just becomes the limit. And I guess it's the absolute value too. I've got to put the absolute value in here. So that goes right here. So that just becomes the absolute value of 2n over n plus 1. And that is 2, because you have the same highest order term in the numerator and the denominator, so you take the ratio of leading coefficients and you get 2. So what you would say is, since the limit as n goes to infinity of the nth root of the absolute value of a sub n is greater than 1, the series diverges according to the convergence criteria of the root test. If this were n plus 1 over 2n, then it would converge because the ratio would be a half. Here's another one. So we have n over 500 to the nth power. So we take the limit as n goes to infinity of the nth root of n over 500 to the nth power. Absolute value so there you'd get n over 500, and that is equal to infinity, because as n goes to infinity, you get infinity over 500, which is still infinity. So Since the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to infinity, the series diverges use the same words here according to the convergence criteria of the root test. Let's see what else we got here. Okay, I think I've already assigned that, but if I haven't, I have now. Maybe I didn't do it, but there's enough missing Friday because of various things. Those are due next Friday. And we will now, so pull out your sheets that we're working on the other day. Yeah, I have one extra copy. That's what I was looking at Seth. He was raising his hand, like, so if he can write it on a piece of paper. Yeah. What's different?
They're just different.
All completely different?
I think this
is supposed to be 9.6.
Oh, 9.6. That's the reason. Yeah. Yeah. Thank you for. Yep. 9.6. Sorry. Yep. I need to fix that in my original thing. 6. Was that why you raised your hand? Did you? Yeah. Oh, you needed that too. Yeah, I don't know where my extra sheet went to. I need to get mine. I need to find the sheet because I don't have. Well, let me look at my blue folder here. I do have the other handouts, the ones with the convergence test. I got extra physics stuff from Friday, but for some reason I don't have. Yeah, anyway, I need to find the sheet so I can write these things down. So we were going through the handout, just kind of deciding which tests to use. While we're at it, we didn't do the second one, and that's because that one was one that would involve the ratio test. So you can write that down, ratio test. Let me copy that to my smartboard thing. So I was trying to think if there's any other you can't use any of the comparison tests because there's nothing that we can rewrite that as that we could use another test to evaluate. It's not a p-series, geometric series. It's not an alternating series. So yeah, we're pretty much stuck with the ratio test. I can't think of any other test that would actually work with this particular series. So go ahead and write that on your paper, ratio test. And the way you would set that up, I'm going to let you work through it. We'll work through each one of these and write out what's appropriate. So we take the limit as n goes to infinity of a sub n plus 1 divided by a sub n. So in this case, a sub n plus 1 is just n, substituting n plus 1 for n. So you'd have 1 over n plus 1 factorial divided by 1 over n factorial. And remember what we did is we take the reciprocal of the denominator. So we have 1 over n plus 1 factorial times n factorial over 1. And you can simplify that. I'm not going to simplify it right now. We'll come back and do it later. Let's see what else. Where were we? What was the last one we actually... where we stopped making comments? Probably that one, right? Is that the one? Let's see what Lexi's got. She was here. Which one did we... where did we get to? Or did we not get that far? I kind of skipped around. Okay. Okay. So the one we haven't done is this one. And we said the root test. Yeah, let's look here. Try to remember. Okay, know what that is. Okay. 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 Yep. Yep. Okay, well, we'll go back and pick up the ones we didn't do. So this, was that the one? I guess that was the one that we hadn't done. N times 3/4. Yeah. So we didn't do this one, so let me copy that. So if it wasn't for the n part, we would not, we would use, that would be a geometric series. So we have r raised to the n power. Remember, p series is n raised to the p power, raised to some fixed thing. So in this case, n is the exponent. So because of the other n, we can't use the geometric series test. And the direct comparison, or the comparison tests, yeah, again, what would you reduce that to? I guess, I wonder if we could do that, you know, if you just drop the n. I guess as long as the ratio, so there's probably two ways. You could probably use the limit comparison test or the ratio test. The one I would choose would be the the ratio test, but you might be able to use the limit comparison test. So I might try that just for the heck of it. So if it was the ratio test, what you would do is you would take the limit as n goes to infinity of the absolute value of a sub n plus 1, which would be n plus 1 times 3/4 to the n plus 1 divided by n times 3/4 to the n power. And if you use the limit comparison test, you first see if the limit, so this is the limit comparison. you take the limit as n goes to infinity of, well, you have to figure out some b sub n that compares to this thing. So you probably would choose b sub n. So a sub n would be equal to the original argument, n times 3/4 to the n. B sub n would just be 3/4 to the n. And if you took the ratio of a sub n over b sub n, or I'm not sure which way it was, but it doesn't really matter because all you're looking for is it's equal to some value. Well, I guess it would be important. I don't remember now. Let's look at my sheet. That's why we have our cheat sheet, so we can look at this thing. So if you look at the limit comparison test, you take a sub n over b sub n. Okay, so I did get there right. I guess the question is, depends upon whether you're trying to prove something's converging or diverging. So let's see what this limit would be. So a sub n would be n divided by 3/4 to the n over 3/4 to the n. And the problem there is that, if you take the limit, if you simplify the expression inside the absolute values, you just get n. And that goes to infinity, so that really doesn't help us any. Unless yeah, so that's why we can't use the limit comparison test, because the term we choose b sub n makes it so that even though we could look at the convergence of 3/4 to the n, it doesn't help because the limit is not finite. So that means that one's not going to work. So that's another reason to choose the ratio test. So what you'd end up with is, I guess the problem, well, no, let's see what we get. We get, so when you simplify this, when you just have n's, they don't really drop out until you take the limit. But 3/4 to the n plus 1 over 3/4 is just 3/4. So we have the limit as n goes to infinity of n plus 1 over n times 3/4 to the first power. And this term goes to 1 when n goes to infinity, and this term just stays 3/4. So it's equal to 3/4. And so I'm going to let you write out, I'll let you write out the reasons why later. But what you do is you look at the sheet and you look for the ratio test, and you'd say, well, the limit as n goes to infinity to the absolute value of a sub n plus 1 over a sub n is less than 1. Therefore, the solution converges. So because that's 3/4, it converges. If it was 4/3, it wouldn't converge. Okay, so that's that one. Let's see what else we got here. Oh, here we go. Okay. So that one we said you use the root test. So again, we'll go back and clean up later, but you can kind of see what's going to happen is when you take the nth root of that, you just end up with n over 2n plus 1. And so the limit of n over 2n plus 1 as n goes to infinity is going to be a half. And we look at our sheet for the root test, and it says if the limit of the absolute value, the limit as n goes to infinity of the nth root of a sub n, if it's less than 1, then it converges. So that one should converge based on the root test. So just write down root test, and what I want you to do, what the procedure is here, is you'll go back in a minute and you will say, oh, okay, yeah, I understand it's the root test. I'm going to look at my sheet. The sheet says blah, blah, blah. I need to write that out, okay? I need to verbally write out why this converges. So it does I'll at least tell you it converges, and you hopefully followed what I said. And if you don't, then you can ask me when we go finish these things off. Okay. Okay, the next one, did we write anything down for that one, Lexi? No. Okay. Anybody have any idea what we might do for that one? Because if you think about it, it's if I drop the 1, the negative 1, I'd have 1 over the square root of n squared. What does that simplify down to? Maya? Yeah, 1 over n. Do we know if that converges or diverges? We've done it a few times. Daniel, what do you think? 1 over n converges or diverges? What is that? What kind of series is 1 over n? P series. Diverge, yeah. So 1 over n always diverges. And the reason I know it, because when we did the integral, you could use the integral test, and 1 over x dx diverges when you integrate from 1 to infinity. So 1 over n always diverges. We see it a lot of times for various reasons. So you could use the, so we know how to evaluate 1 over n. We know that diverges. And because we're subtracting 1 instead of adding 1, we can't use the direct comparison test, because the simplified expression b sub n would be in the wrong direction as far as the sign was concerned. Well, actually, is that true? Yeah, I think so. Well, the limit comparison test works good anyway. So this one, you would use the limit comparison test. So let me copy that to my sheet here. Okay, let's try it again. I was just thinking if there's any other tests you could use. If you use the ratio test, you get an inconclusive result. So anyway, use the limit comparison test. And b sub n would be equal to 1 over n. Okay. So let's see what we got now. Did we do that one? Nope. Okay. I don't think we did any of these. Okay. This one actually should be able to recognize as one of the earlier things that we looked at. So, Seth, what kind of series is this? Do you have your sheet? Yes, yeah. So it's a geometric series. You have r to the n. So in this case, r is less than 1. So I'm going to let you guys figure that one out just by looking at the sheet and look at the r value of r. 6, the only thing 6 does is it affects the actual sum. You can in this case, you can figure out what the sum is. So I'm just going to write down geometric series. You can look at the rule for geometric series, and I want you to put what the sum is in that one. Okay, next one, this one. So, Kreia, I'm going to ask you. So this also is one of the earlier ones that we did. It is, yeah. This is the one people, if I rewrote it, I'm sure you'd know the answer. So I'll write the answer. I'll give you, well, actually, is that true? Oh, yeah, right. So let me write this as Okay, now what is it? Yeah, yeah. So Craig says it's a geometric series, which is correct. So sometimes you're full when they just have some number raised to the n power in the denominator, but you always have 1 raised to the n power in the numerator. So once you've done that conversion, you can see that it's a geometric series. So use the geometric series test, and you can also find out what the sum is. Same way here. Okay, so you can use your sheet to figure that one out. Okay, next one. Okay, Xavier, what do you think? Okay, let me give you a hint. So we just talked about that. Let me go back and show you one. Uh, yeah, see there's n over 2n plus 1 to the n power. Natural log of n over n to the n power. Okay, so it's a root test. Yeah, that's correct. Okay, so it's a root test, and all you have to do is take the limit, ultimately take the limit of that as n goes to infinity, and if that is, let's see what it says. It says the root test, if it's less than 1, then it converges. If it's greater than 1, it diverges. If it equals 1, so all you have to do is take the limit as n goes to infinity of the nth root of the natural log of n over n to the n, absolute value. So that just becomes the limit as n goes to infinity of the natural log of n over n. And we've looked at that before. You can use L'Hopital's rule. You can look at just the magnitude of these two. Okay, I'm not going to answer that yet. I'm going to let you think about it, but hopefully you'll remember what it is. Okay, here is another one. We just did one very similar to this. So, Hannah, so what do you think? Which test? Yes. Huh? No. Okay. What if I drop the -1? What is the series? 1 over n. So we just did something like that. This was actually a little easier. So if we go back and we look at this one, okay? So here we did the same thing. We had 1 over the square root of n squared minus 1, which if you drop this, it becomes 1 over n. And we said that diverged. So as long as this limit is not unbounded, then it's going to converge. So you do the same thing right here. You'd use the limit comparison test, where b sub n is 1 over n. You can't use the direct comparison test. If I added 1, I could use the direct comparison test. Actually, maybe you still can use the direct comparison test. Yeah, I think you can. Well, let's think about that. I got to think. So, in the direct comparison test, we know that 1 over n diverges. So we're going to use the diverging thing. And so all we have to do is to be able to use that, this has to be true. And if b sub n equals 1 over n and a sub n is equal to 1 over n minus 1, if you stick that in there, b sub n 1 over n, a sub n is 1 over n minus 1. Cross multiply, get n minus 1 is less than or equal to n. or -1 is less than or equal to 0. So that is true. So you actually could use the direct comparison test because this diverges and this is always smaller than that, then if this diverges, then that diverges. So in this case, you could use the direct comparison test, or you could use the limit comparison test. Either way, they both tell you it diverges. Okay, let's move on here. Here we go. Okay, this one should be easy because it has this -1 in front of it, which makes it what kind of a series? So, Cassie, what kind of series has a -1 raised to a power in it? Look through your list. There you go. Alternating series. So it's an alternating series, so all we have to do is do two things. We have to show that a sub n is equal, the limit of a sub n as n goes to infinity is equal to 0. So remember, the a sub n is the part that's not the -1 raised to the power. So a sub n is not the whole thing, it's just the non-alternating part. So you have to take the limit as a sub n of a sub n as n goes to infinity, and if that equals 0, that's one check. So you see that happens. As you let n go to infinity, you get 1 over 2 times infinity minus 1, which is infinity. So that's true. And the other one is that a sub n plus 1 has to be less than or equal to a sub n. And again, you could just try some numbers out and see what happens, or you could take 1 over 2 times n plus 1 minus 1. Is that less than or equal to 1 over 2 times n minus 1? So you get 2n minus 1 is less than or equal to 2 times n plus 1 minus 1. And you get 2n minus 1 is, so you get 2n plus 2 minus 1. And you see the 2n's cancel out. So you get -1 is less than or equal to 1, which is always true. So both this is true and that's true. So because of that, this series converges. It's an alternating series. It satisfies the requirements of the alternating series. So that one works. This one you use the ratio test. I should have told you that. I should have asked you to do it. But because this is one that is kind of a combination of two different kinds of functions, it's where n is the base and where n is the exponent. So that really limits us to one test, which is a ratio test. And I think we have one more. So let's see what we got. Or is that the last one? Oh, one more. Okay. So here we have Asia. What kind of test do we have? What kind of series do we have?
Maybe alternating.
Yep. So it's an alternating series test. So you have to apply the same rules that we just did previously. You have to look at the limit of n over n squared plus 1 as n goes to infinity. Is that equal to 0? And also, is a sub n plus 1 always less than a sub n? I know what the answers to those questions are, but you need to do that. So let's go work our way backward now. Okay. So what I want you to do on this last problem is to apply the two criteria for an alternating series. So write those out, come up with some conclusion. Once you have addressed the two criteria for the alternating series, then you need to write out a comment, write something out. And we've done this quite a few times, so you can look at the notes and try to come up with something. All you English people, this is your opportunity. This is your one writing assignment for the calculus, is to write out the justification for your conclusions. So it'll be something like, since this is an alternating series and this is true and this is true, the convergence criteria for the series are satisfied, hence the series converges, something along those lines. So go ahead and give that a try. Do it yourself. I'll give you a few minutes. You can ask me questions if you want to, and then I'll write them out. But on the test, when you test it on this, you have to do that. You have to verbally write out why you've made the conclusions that you have. Well, you can simplify it. What you could do is you could use the L'Hopital's rule, and then, because right now you're indeterminate, you're infinity over infinity. Even though you're infinity over infinity squared, it's still technically infinity over infinity. So if you take the derivatives, then it won't be indeterminate anymore. You can also think that, infinity squared divided, it's, yes, go ahead.
Why does the inequality of a sub n plus 1, or 0 is less than a sub n plus 1 is less than or equal to a sub n have to hold true for all n? Like, could it not just be for some n is greater than some?
Yeah, I know. I have the same concern. It seems like it ought to work that way, and it bothers me when it does that, because remember we looked at one, I think that the first term was different, but all the other ones are less, and the first term's not going to make it go to infinity. So it seems like there ought to be some after. Yeah, I agree. I think after some n, some capital N, if it's less than, because it's those terms as you go out way out there that affect the convergence. It's not whether one is a half versus 3/4. That's not going to really affect it. So yes, I agree with that, and I don't know why they say that, but I think in most cases it turns out that's true. That I mean, in this case, I think it works for all values of n. But yeah, there are a few weird cases where it doesn't apply for all n. Yeah, this is one case where it's not quite so easy to use this approach to prove it. If you wanted to, it would be acceptable if you just made up a table with n equal 1, 2, 3, 4, 5 maybe, and show that the first few terms of the series it's satisfied. If you didn't feel comfortable trying to prove this is true, I'm going to try it anyway because I just want to, but this would be more, this is probably the most complicated one we have to determine whether a sub n plus 1 is always less than a sub n. I was just checking my math. Thank you. So, yeah, you can see if you start at n equals 1, you're going to get 1 plus 1 is 2, minus 1 is 1. So that's, for the case of n equals 1, it's true. You get 0 is greater than 1. N equals 2, you get 4 plus 2, which is 6, minus 1, which is 5. So, yeah, I still had to stick some numbers in there. There may be some way of showing that. Anyway, it's true. Okay, so you can see what I've done is I've taken this part, that's a sub n. I've taken the limit as a sub n as n goes to infinity. I used L'Hopital's rule to reduce this down so that it was determinant. So 1 over infinity is 0. So it satisfies the first requirement. And then I looked at whether a sub n plus 1 was always less than a sub n, which turned out to be true. So then the way you would write this out is since this series is an alternating series. So first thing we do is we identify what kind of series it is, if it's appropriate. Okay, since is an alternating series, and the convergence criteria of the limit of a sub n as n goes to infinity equals 0, and that a sub n plus 1 is always less than or equal to a sub n are met, the series converges. Okay, so that makes sense. Since this is an alternating series and the convergence criteria of the limit that a sub n as n goes to infinity equals 0 and this are met, the series converges. Seems good enough for me. Okay, so let's move back to the previous one. So we said that one you use the ratio test. So again, look at your tape, look at your sheet, look at the ratio test. So you're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. See whether that's less than 1, greater than 1, or equal to 1. If it's less than 1, you'll say something like, you won't identify it as a certain kind of series. You'll just say, according to the convergence criteria of the ratio test, the limit, well, you could say something like, because the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is either greater or less, whichever one it is, which satisfies the criteria. If it converges, you can say satisfies the convergence criteria, or you can, if it diverges, you could say it satisfies the divergence criteria. Therefore, the series converges or diverges. So I guess the snow is still not sticking. I'm going to take a walk out and see what's happening. Yeah, it's not snowing like it was earlier. So shouldn't be any problems. Now, when you get to the part, you may think, what do I do with n cubed? Do I have to multiply n cubed out? And probably not, because ultimately you're going to evaluate n plus 1 cubed over n cubed, and that's going to be 1. Okay, so most of the cases where you do have something n by itself, or n plus 1, or anything really involving n raised to some power 1 or anything, you really can't simplify it. So you end up just treating that ratio separately. And if you did multiply it out, you'd have n cubed plus 3n plus 3n squared plus 3n plus 1, or plus 1, but the lower order terms don't really make any difference. So if you wanted to multiply it out, you could, but you don't need to multiply it out. So remember, you take this reciprocal of that, multiply it by that, and simplify it. Yep.
Did you make a copy of this, the worksheet thing?
Oh, you didn't get one either?
No.
Oh, okay. Yeah, I couldn't remember how many people didn't get it. And I only found one copy, so I thought maybe I'd just one person, but it's more than one person. Yeah, okay. I'll do that. You also need one too? Huh. I wonder where they're all hiding. Okay. Yep. Let me do that. Yeah, because we'll be working on it. What I'll do is let me see if I'm connected to the network printer. I might be able to print it out right now and go and get it for you. Yeah, it looks like it. So let's. How many copies do I need? So, Crea, Michaela, Seth. Oh, and Kelly too, huh? Okay. Oh, you did have one. Oh, okay, okay. So I'll print 4 copies of it. So I'll get that during physics, and you guys can. So anyway, there you go. The key thing was this term here. This one ends up just being, like I said, 1 if you multiply that out, the ratio of leading coefficients. And so 2 to the n divided by 2 to the n plus 1 is 1 over 2 to the first power. And so when you take the limit as n goes to infinity, the ratio is a half. So then you go to your convergence criteria for the ratio test, and it says if the limit of the absolute value of a sub n over a sub n plus 1 over a sub n as n goes to infinity is less than 1, then it converges. So then you write out the corresponding verbiage that goes along with that. So it's kind of like, what you need to do is look at the last one and try to come up with something that sounds similar to that. So let me grab that. A lot of times is using previous experience to figure out how to write this. So in this case, it's not a, we can't identify it as a alternating series, but what we can say is that something like using the ratio test, we have shown that the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is equal to half, which, according to the convergence criteria, indicates that the series, the summation from n equals 1 to infinity of whatever the original series was, forget what it was, n cubed over 2 to the n converges. Okay, using the ratio test, we have shown that the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to half, which according to the convergence criteria indicates that the series converges. And probably it would have been better to actually, let me just insert something. Probably what I would do, I'd do something like this, just to be more explicit about what the convergence criteria is. So because it's less than 1, so since 1/2 is less than 1, it satisfies the convergence criteria, which indicates that the series converges. According to the, yeah, doesn't have to be perfect English or anything. Otherwise, I'd be in trouble. Okay, so let's back up on here. So we said this one was an alternating series. So didn't we do that? Was the last one. So I think we've already shown, yeah. So what you probably should do is take this description and just apply it to this. So as long as you have written out explicitly that this is satisfied and this is satisfied, then you just need to write the words out that go along with that, which seem pretty much the same as you would have written in the last problem. So just take that problem and add this verbiage, except change it so the alternating series is not that one, but the one that's the subject of that particular problem. Okay, so that's it for today. We will continue on backwards, moving backwards in time, finishing out all the nitty-gritty details of each one of those previous problems that we looked at.